Did I correct this on your notes? Or is it, no? So if the probability of A and B, so remember that symbol in between means and, that's the intersection. If that probability is 0, does it make sense that the two things do not intersect? So then you have a circle A and a circle B without that overlap. We call that mutually exclusive. Two things that cannot happen simultaneously. Okay? You cannot be in both Manitoba and Alberta at the same time. Well, okay, don't get creative. We're not going to cut anybody in half or anything like that. Right? So we would consider those events mutually exclusive. Your probability formula for OR, the addition formula, usually has this in it, minus the probability of A and B. And you can keep that in it. I wouldn't like memorize a new formula. I would probably remember the regular formula, but the regular formula, when you add A and you add B, you always added the middle section twice. So you have to subtract the middle section once. That was your addition formula. But if they don't ever overlap, then you could just find the probability of A and the probability of B separately. So other mutually exclusive events, right? You roll one die and getting a 1 and a 3 can't happen at the same time. So when I'm asking what is the probability of rolling a 1 or a 3, well, common sense, you just say it's 2 out of 6. Technically, we could say, well, one of them was 1 out of 6, and the other one was 1 out of 6, and adding them together is 2 out of 6, making the total. And we don't even have to subtract the chances of rolling a 1 and a 3 simultaneously, because that's impossible. So some of these questions, I think you would go to your common sense and just say, I can figure this out. Card is drawn at random. What is the probability? It's an ace or a king. That or is important because it could be an ace or it could be a king. Could you do this without any formulas? How many are there? 8. So good. I'm glad you could just get 8 out of 52. Did you have to use you want to use the formula? No, but you could. Probability of ace or king could be probability of ace plus probability of king minus the probability of both of them. But you can't get the ace king. There's no ace king in the cards that has both of them on it at the same time. So for this, right, probability can sometimes be very intuitive. And we are going to find out today that probability can sometimes be very unintuitive and not what you think, and weird answers and fun. Okay. But we'll continue getting all of our definitions before we get too crazy. So far, life is good, life is simple. A sample space diagram, a way of showing all the possible outcomes. Rolling 2 dice. I so badly want to get into questions that are a little bit weird. We'll wait just a little bit. So, rolling 2 dice. Smallest number I could get is 2 1s, right? Biggest number, 2 6s. How would I show all of them? I could make a diagram like this. It's kind of annoying, but does that make sense? And sort of, this is, draw a thicker line here and a thicker line here. This shows 1 dice This shows the other dice. And you make a diagram to show all 36 possibilities. What are your chances of getting a 6? Well, when you've got all of them listed, it's going to be easier to figure out these questions. Little bit of regret that I didn't just copy this into your notes, because it's not hard to write down. Don't know how much learning you got while writing it down. Hopefully, really got a sense of all 36. So this shows you why 7 is the most probable number to roll. Right? If you had to guess, what am I about to roll? Your best chance of guessing right would be to guess. But it's not guaranteed, right? Because a 7 happens 6 out of the 36 times. 6 happens 5 out of 36 times. How many doubles are there? We can now answer questions like, now that we see that there's 6 doubles, and we just talked about there's 6 sevens, you could like, whoa, I'm always scheming how to make money off your friends. You could ask your friend, which do you think is more likely, rolling a 7 or rolling doubles? I'll give you $1 if you get it right. It's kind of mean, isn't that question? Because they're the same. But you kind of imply that one is more. You probably win it all, right? If you win enough money, then you can give me a commission. Okay. Scoring less than a 6. Well, then you would count up the 5s, the 4s, the 3s, and the 2. Adding those up, there's 11 of them. 11 out of 36. Scoring more than 8 or an even number, and I guess if you wanted to show work, so scoring more than 8, I'll circle those in red. Or, we have the word or, this is different than the word and, so we have to pay attention to that. Or an even number, so we would also include our 6s, our 4s, and our 2. You see, I don't have to circle the 10s or the 12s again. If I did, it's not wrong, right? But in the end, I just have to count the ones that are circled. Don't need a formula. Just figure out that there's 24 of them. Oh yes, thank you. I would also circle the 8s to get all the even numbers. And sometimes it's going to be easier to count the opposite. If I had asked how many are even or more than 4, can you see the only thing I'm not counting is the 3s? It'd be much easier to say, well, there's 2 3s, so since there's 36 in total, there'd be 34 that are even or bigger than 4. So sometimes we can use that as a counting strategy. Coin is tossed and a dice is rolled. What is all the possibilities? So we just have to put all the possibilities together. You could get a 3 and tails, or you could get a 3 and heads. So as far as listing them go, you just have to come up with some sort of chart or way of listing. Can you see that there would be 12 of them? Because there's 2 for heads and tails and 6 for the dice, giving you 12 in total. Once you have that chart, it's really easy to see what's the probability that you obtain a head and a number less than 3. I'm not even going to show the extra work because I hope that these ones are just intuitive and straightforward. We could make an ugly formula and write way too much information, but we don't need to. It's really easy that head and, again, we're looking for and here. If it said or, you'd have to include all the heads and all the numbers less than 3. So we can write it heads and less than 3, 2 out of 12, or 1 out of 6. Now we're going to get into some of the definitions that are a little bit more technical. 2 events are independent if the occurrence of one does not affect the occurrence of the other. And this is sometimes something that is misunderstood. For example, if I flip a coin, what's my chances of getting heads? 50%, right? Flip it. I got tails last time. It's supposed to be 50%. Should I get heads this time? Am I more likely to get heads this time? Because I got tails last time, and it should be 50%. I got tails. Now I've gotten tails twice. Now, for sure, what is the probability of getting heads this time? Must be better, because it's really unlikely to get tails 3 times in a row. No. Each time I flip this coin, this is an example of an independent event. It doesn't matter what has happened before. Each time I flip it, I've got a 50% chance. So that would be an example of an independent event. Okay? An example of something that's not independent. Right? Okay, first of all, what are the chances that you get an ace? 4 out of 52. Did you get an ace? Okay. Now, what are your chances of getting an ace? 4 out of 51. See, it changed. Why? Because a card got taken out. This would be considered dependent events because your probability depended on what happened here. If I took her card and put it back in, and then got you to pay, then it would be independent again. It wouldn't matter what the person before if the card went back in. So we have ideas of independent and dependent events. And when things are independent, probability rules are really straightforward. So here, a dice is rolled and a coin is tossed. For sure, this doesn't affect each other. These would be considered independent. We have a product rule for independent events. And this is usually when things happen one after another. What is the probability of getting heads and then heads again? Well, I have a half chance for the first time, a half chance for the second time, so getting 2 sets of heads in a row would be 1 out of 4. 1 half times 1 half. You just multiply the 2 probabilities together. So card is randomly chosen from a deck of 52 cards, and a fair-sided dice is thrown. Find the probability that the card is a jack and a 5 is thrown. So you want to find the probability of jack of spades and 5. Jack of spades would be 1 out of 52. 5 would be 1 out of 6. This would be 1 out of 312. Is it very likely? This is the other thing that's interesting about probability. Is, right? Would you pay $5 to play this game? Sure. Sure. So if you get the jack and the 5, you win your $5 back. I'd be doing very well in this game one time. I wouldn't have to pay out very. If we played, what this probability means, if we played this game 312 times, theoretically I should lose once. But I should win 311 times. Now, it's not guaranteed, because you could. Here, flip the coin first. Oh, that's not a coin. We have to die. Here. Let's add the intensity roll. Try again. No, it's not. You're supposed to get 5. That doesn't. Unbelievable, actually. He got a 5. Amazing. Now, if he gets the jack of spades, he wins his $5 back. It's pretty unlikely to win this, right? We just even rolling the dice. But in a lot of lotteries, 1 out of 312 is a really, really good chance. When you think about the main lottery, Lottery 649, that number on the bottom is about 14 million. Your chances of winning are so low that it's almost impossible. But the reason why someone usually wins is because across Canada, they sell more than 14 million cards. So when you've had, if we did this 312 times, wasted all class, just tried over and over again until someone would eventually win. But it might take a long time before that happens. But when you see it happen once, in something simple like this, your brain would tell you, you know what, you are not going to win. Everything is telling you that you are not going to win, because the chances of getting it right are not going to happen. I didn't get it. I was going to roll a 5 and randomly pick the jack spade, and everybody would go crazy, but it didn't. Oh. Once it did happen to me that something crazy like that happened. I've got this puzzle called Instant Insanity. The Instant Insanity puzzle is just 4 cubes here with red, blue, green, and yellow on them. And your job is to stack them so that you have a color showing. There we go. Red, yellow, blue, and green, all on one side. But then you have to turn it, and you have to have all 4. Oh, I screwed it. And all 4 on this. And if you do it at random, the first one you can put down in 1, 2, 3 different ways. Then after that, each of these can be put down in 24 different ways, whether you have it this way, depending on which of the 6 sides you put it on, and each side could be rotated 4 ways. So each cube put on top is 24. This is like permutations and combinations question, right? First one can be put down in 3 ways, then 24 ways, then 24 ways, then 24 ways. So your chances of getting it right if you do it at random is 1 out of a very big number. And I just grabbed them and put them like this and rotated them so one side worked, and I turned all the sides to the class. I just was like, and they were like grade 9s who had no idea of mathematics, so they're like, sounds like a stupid easy puzzle. So Yeah, so sometimes crazy things can happen. I would have much rather won the lottery, but this was exciting. You'll have to try the puzzle sometime. Okay? This is not on bag, but one bag. One bag contains 3 red and 2 white marbles. Another bag, 1 red and 4 white marbles. A ball is selected at random from each bag. Can you see that this is independent? That picking out of separate bags won't make an effect on the next choice. So what is the probability that both marbles are red? Well, your chances of getting a red marble in the first one are 3 out of 5. Your chances of getting a red marble in the second one are 1 out of 5. Does it make sense that your chances of getting both red marbles, and I guess we could say, write that notation as red and red, would be 3 out of 25. And this is where your skills in permutations and combinations is going to come into effect, because in part B, what's the probability of getting marbles of different colors? What would have to happen? What could I pull out of the first one? I could pull a red one out of the first one, and then I would have to pull a white one out of the second one. So that would be shown as probability of red and white. The red one was 3 out of 5. The white one is 4 out of 5, giving me 12 out of 25. This isn't the right answer. Why is 12 out of 25 not the right answer for this question? You could also have a separate case. You do the white one first. Remember cases in permutations and combinations? When you can't count something all at once, you count it separately. And white first would be 2 out of 5, and red second would be 1 out of 5, which gives you 2 out of 25. And you add your cases up to get 14 out of 25. Boy, I like the word on today. At least on marble. This way. This is supposed to be 1. If at least one marble is white, we could do cases here. What are the possibilities? White then red, red then white, or white and white. You could figure out those 3 altogether. However, sometimes there's a shorter way to do that. So option 1, just so that we could, that's probability of white and red, probability of red and white, probability of white and white. Well, white and red we figured out already to be 2 out of 25. Red then white we figured out to be 12 out of 25. And white will be 2 out of 5 times by 4 out of 5. 8 out of 25. And if you added all of those up, you get 22 out of 25. Can you see how part A gives us a shorter way? The opposite of at least one white marble is no white marbles. And the word that we used for that before would be like the complement of. So the opposite of at least one white marble would be 1 minus the probability of red and red, which we already figured out to be 3 out of 25, would also give us 22 out of 25. Have you ever seen a 4-sided dice? they are, of all the dice that exist, my least favorite to sit on. Because they're little pyramids with a very pointy part at the top. They have 4 triangular sides. I have no idea what this dice is from. I have it as a puzzle, internet search puzzle. What game comes with a green 4-sided dice where every side has the sides labeled with 1 number missing? I'm not sure, but I have it, and I don't get to sit. So if you have a 4-sided dice, and you labeled the sides 1, 2, 3, and 4, you could make a dot, and then make a sample space of your 4-sided dice. So in this case, the most likely number to roll would be 5. Event A is the sum of the 2 dice is 6. I've circled those in red. Event B, the number on both dice is the same. So I've circled those in purple. Find the probability of A and B. So this is the and sign. That means they both have to happen. How many times do they both happen? Oh, this is not good. I've got to put that pen down. Here we go. 1 time out of the 16. A or B means it could be one or the other. You just count how many numbers you've circled in total. We've circled 6. So it would be 6 out of 16. Now, definitions-wise, are these events mutually exclusive? Are they independent? How would you justify it? First of all, I think the mutually exclusive one is the easier one to answer. Mutually exclusive means they can't happen at the same time. But when we look at the circled parts, and we look at the probability of A and B and A, they can happen at the same time. So we would say they are not mutually exclusive. Independent is a little bit harder, especially when things are happening at the same time. Independent, usually when we do independent stuff, something happens and then something else happens after. But sometimes there's independent questions like this where they happen simultaneously. Are they independent? Well, what we'd have to check is we can use the formula for independence. If they're independent, the probability of A and B would equal the probability of A times the probability of B. We know the probability of A and B is 1 out of 16. We can figure out the probability of A times the probability of B, because the probability of A is 3 out of the 16. The probability of the B is 4 out of 16. When they get multiplied, we get 3 out of 64. Those things aren't the same, so we would say that they are not independent. And now we we get to have some intriguing and probability, which doesn't go necessarily to how your intuition works. And first of all, we're going to do what's called the famous Monty Hall problem. Famous Monty Hall problem is that you've made it to the end of a game show, and everybody who makes it to the end of the game show wins a prize. And the prizes include either getting a brand new sports car, like super expensive, or a live goat, which I don't know what you would do with if you won. And they show you 3 doors, and the goats, like, it's very soundproof, so the goats don't say you can't cheat by like this or anything like that. But behind 2 of the doors are goats, so your chances of winning a goat are much better than your chances of winning the nice car. So I have represented the goats with jacks and the brand new car with an ace. Okay? So the way that this game works since you're looking this way, does this make sense for you as door 1, door 2, door 3? The way that the game works is you pick a door to see which prize you want to win. Which door would you like to pick? 1, 2, or 3?
1.
She picks door 1. After she picks door 1, I say, oh, it's good you didn't pick door number 2, because door number 2 was a goat. But I'll give you another chance. Do you want to stay with the one you chose originally, or do you want to switch to the other one? You're going to switch. Okay? She switches, and she won the brand new car. You know this problem.
Yeah, I know.
Okay? So you think switching is better, or does it not really matter? Our intuition would say it shouldn't matter. Can you see how your gut might say, well, now that the goat is in 2, what are your chances of getting something right? 50-50. So why does it make a difference for switching and staying? But the question is, what are your chances of winning if you switch? Okay? You switched and you won. We'll do some theoretical probability here. Door 2. Picks door 2. I showed door 3. Want to switch or stay? Switch. So we're going to always switch to C. So now switch to 1 again. All right. So we got 2 people going home with 1, 2, or 3. 3. Good thing you didn't do number 1. Are you going to switch? You get to go home with the goat. So you lose, right? 1, 2, or 3? 2. Good thing you didn't pick number 1. Switch. So now we've done it 4 times, and we switched and won 3 times. So experimental probability says switching wins 75% of the time. Is that the answer? Would that, no, it's not the answer. Experimental probability is close maybe to the answer. It seems like switching is better, but how do we figure it out exactly that switching is better? What has to happen first for you to win when you switch? You have to pick a goat to begin with. What are your chances of picking a goat to begin with? Not 100%. This is not a goat. Obviously, a sports fan. Look at it. Come on. 2 out of 3. You have a 2 out of 3 chance of picking a goat. And it doesn't matter which goat you pick, because I always show you the other one. And then switching will automatically win. So in this case, when I put it that way, if you pick a goat, you win. Your chances of winning are 66.6%. Picking the right car right from the beginning is only a 1 in 3 chance. 2 in 3 chance that you'll pick a goat to begin with, and then switching is better. Now, there are people that argued long and long, no, it does not matter. And what I would say, they're like, it has to be 50-50 because you only have 2 choices left and you have to win. And the best way to see this as differently is imagine we played this same game, but we had 100 doors instead of 3. With 99 goats in 1 car. You pick a door. Then I show you 98 other goats. And you have a decision to switch or to stay. And I hope if you see 100 doors, that it becomes really obvious that switching would be better. Because your chances of picking the car right at the beginning would be really rare. And then switching for sure would be better, especially if I showed you 98 doors that were all goats. One more to make you think. I'm going to tell you that 1 die is a 2. What are the chances I rolled a 7? What does your gut say? I told you that 1 of them is a 2. What are the chances I rolled a 7? Right? First of all, we have to recognize what would seem logical and what our gut would say, and it's going to be wrong. So feel free to say what you think. Seems like a good, easy, logical answer. What are the chances? I rolled a 2. Told you 1 of the dice is 2. What are the chances I rolled a 7? Okay, 1 and 6. Good, that is well. But that is what your gut should say, because what does the other dice have to be? 5. And your gut says if the other dice has to be a 5, what are the chances of getting a 5? 1 out of 6. Okay? This is where conditional probability, the goat won a little bit, but this one I think even more. Okay? If I roll 2 dice, and I specifically have 2 different colors here for this purpose, when I told you 1 of them was a 2, can you see that the 2 could have been on the white dice, or could have been on the red dice? It actually makes a difference. Because if we go back to, had it, most, wait for it, we had it somewhere here where we had all the numbers written. Here we go. If we go back to this chart, as soon as I give you some information, I hope that when I told you that I rolled 1 of them was a 2, your brain would have said, oh, I'm pretty sure he didn't roll a 10 in total. Why? Because if 1 of them is a 2, a 10 is impossible. You can't roll an 8 on the other dice. So as soon as I tell you 1 of them is a 2, your sample space gets restricted. What is it restricted to? Well, let's have some. Let's take out this pen, yes. Can you see that this is not possible? These are not possible. These would go away. And these would go away. If I tell you 1 of them is a 2, those are your only possibilities. What are the chances I rolled a 7? Could have been this. Could have also been this. Because I didn't tell you if it was the white dice or the red dice that was a 2. And that's specifically why I have 2 different colors here. What's your probability when you look at the chart now? 2 out of 11. Your brain would have never have said, oh, I know the probability is going to be something out of 11. That's what I really feel would be lucky in this case. Now, if I had rolled them and I said, oh, I rolled a 2 on the red dice, then this is a different question. Because then, if red is represented by yellow here, that would take out those ones, and now it's a 1 out of 6 chance. But if I don't tell you which dice has the 2, then there's 11 possibilities, and it's 2 out of 11. And this is an example of something called conditional probability. You're finding the probability when a condition is given. And the condition that's given changes your sample space. Normally we had 36, but as soon as I tell you one of the dice is a 2, I reduced it to 11. Right? We could do other things. I could say I roll one of the dice is an even number. What are the chances that I rolled a 7? So then you would go to your chart here and say, well, if you gave me that one of them was even, what would that take out? That would take out these ones. No. One of them. Oh. Whoa. Whoa. Okay. Let's go again. What would it take out? It would only take out, this is not a possibility. This is not a possibility. This is not a possibility. This would not be a possibility. Everything else would be okay, right? Just the double odds would be taken out. So you would take out 9, leaving you with 27 possibilities left. If one of them is even, what are the chances I rolled a 7? 6 out of 27. So the condition reduces our sample space and changes our probability to be less intuitive. Okay. Oh, I so badly want to just teach conditional. We'll get there. Compound events. 2 or more simple events. 3 boxes contain white, black, and red marbles. Box 1, box 2, box 3, and how many are in each one? A box is chosen at random, and a marble is selected. Something you might have seen in your permutations and combinations unit was tree diagrams. We can draw a tree diagram for this. The way that it would look like is, what do you do first? You choose a box. What do you do second? You choose a marble. So we show our first thing has 3 choices because there's 3 boxes. So we draw 3 branches, and that's why these are called tree diagrams, because we call them branches, and trees have branches. And then, after that, you choose marble, so each branch would have 3 off of that, because it could be white, blue, or red. To find the probability that you get a red one, you see in the end, there's 3 different ways you could get a red, either through box 1, box 2, or box 3. And on each of the branches, you write the probability of that branch. So we're going to assume each box is of equal chance to choose, so that's why there's a 1/3 on each of those branches. And then, in box 1, there was 8 out of the 16 were white, 2 out of the 16 were blue, and 6 out of 16 were red. So we write the probabilities on each branch. So the probability of getting a red, if we really wanted to write things out formally, you could get a 1 and a red, a 2 and a red, a 3 and a red, which Figuring them all out would be 7 out of 24. Add up all of your cases. If you changed it to a decimal, you'd go to 3 sig figs. So how will this change into a conditional probability one? All right, we could say, Natalie says, ooh, I got a white one. What are the chances she picked box 2? Is it still 33%? Or if she got a white one, would it be, it's like more likely in box 2 to get a white one. What are the chances she picked box 2? If she said, I got a white one. So we're going to have to figure out how we can use that extra information that was given is going to change our sample space and change our probability. Used to be in the old grade 12 pre-calculus, they would have questions like this with marbles, but instead of saying box A and box B, they would always say an urn, which is like the same kind of thing you put ashes of dead people in. So it was kind of eerie. They're like, oh, let's play a game. Let's go get grandma and grandpa and throw marbles in there. What did you get? Okay. So, box A contains 4 red balls and 3 green balls. Box B, 2 red and 2 green. Can we draw a tree diagram of this? Yes. What do you decide what you're going to do first? Choose from box A, then choose from box B. It really doesn't matter which thing gets done first and which second, but for drawing your tree diagram. And then once your tree diagram is drawn, you can highlight, oh, there's 2 different cases where you could get marbles of different colors. Can you see that these are independent events? That choosing from one box doesn't affect the probability of choosing from the other box. That would be terribly memorable if I did bring in like fancy vase-like things with ashes and marbles. Even if it was just ashes from the fire. Everybody good? Last call for what? Plus. What's that? Okay. Whoever knows, they better go, right? Okay. Okay, try this one on your own. I'll put the answer up in a second. Quick check on part A. These events are dependent because it's successive. Notice the probability on the second branches was affected by the probability on the first branches. And for part B, how many people did it this way? How many people did it this way? You could do all three cases, add them up, or you could just subtract the opposite case. All right, you can check your answers for number 4.